Okay, let's start lab 7. This week, we want to experiment with a sample code simulating the two-dimensional lattice Boltzmann model. You will be asked to apply some simple optimization to this code we have here. After that, in the second part of the lab, we experiment further with the parameters of the simulation. You can download the code from link we have here. So in this link, we have the full implementation of the two-dimensional lattice Boltzmann model. As you can see here, we have here the number of iterations, the size of lattice, the number of states, some parameters related to the anyway, these parameters characterize the fluid. Some constant weights. If you remember, we have W and C weights, which are constant values, and we used to obtain we use these constant values to obtain the here to obtain the local velocity of cells. As we can see here, we have some constant C values, and we have some constant W values, and all of those constant, you can see some of them here, and we will initialize some of them in the initialization step. Anyway, you can see lots of variables here and parameters. So as I mentioned, you can download the code from this link. In this lab script, as shown here, you can see an outline of the main method along with some notes about the code which you might find useful. This piece of code here does some initializations and populate the lattice by initializing the F in arrays in the grid. So this part of code do some initialization step. There are some other tables and arrays initialized here, such as this no sleep, I1, I2, and I3. If you look at the the full implementation, you can see we initialize those tables here. I should say that these data structures here are used in the implementation of boundary conditions. In this example, we have an obstacle located in the middle of the grid. Boundary conditions include the behavior of the particles in the simulated fluid, once facing the obstacle sitting in the fluid. So if you simulate the grid, like previous weeks, you will see a lattice, including some particles. At the middle of this lattice, you will see an obstacle. So using these boundary conditions, we will simulate how particles or how the state of particles change once collide with this obstacle at the middle of the lattice. So anyway, we have some boundary conditions to update the cell states when collide with this obstacle. We will discuss boundary conditions in the following weeks. So please ignore everything related to the boundary conditions this week. and just run the code. Anyway, we will discuss boundary conditions in following weeks. After the initialization step, the simulation starts. In this for loop, we obtain the new generation of the grid by applying the cellular automata rules, as discussed in the lecture. So in the lecture, I explained that we have two sets of rules, collision and streaming rules, to obtain the next generation of grid. Here, we first calculate the local density and flow velocity of each cell, as we can see here. We obtain these values based on the formulas on slide 12. So using these two formulas, we obtain the local density and local velocity of each particle. Then particle states are updated using collision and streaming rules. So to obtain the distribution values after collision, we use this formula we have here. Okay, in this code, we have some omitted blocks highlighted with BC code. So this BC code we have omitted here implement boundary conditions. This BC code or boundary condition code calculate how particle states change after colliding with the obstacle at the middle of grid. So anyway, we only run this piece of code and we don't care about the operations they are doing. You can so ignore this code, this piece of code, until we have discussed these matters next week. Okay, so as I explained, we have some initialization step, then simulation start. We calculate the local velocity and local density of cells. Then to obtain the next generations of grid, we apply this collision and streaming steps. In the first part of this lab, please run the code for instance, here we have 5,000 iterations. Please run the code for 5,000 iterations to see how the velocity of the flow changed during the simulation time. If you run the application, you can see a lattice including some red and blue points. Red particles represent fast flow, while blue ones show slow speed particles. So anyway, you please run this code and see how the particles move in the lattice. In today's lab, I want you to optimize the code. In the code, we have for loops like like this one. We have for loops like this one, looping over the 9 velocity states. So as we can see here, this loop scan 9 states we have. Q is equal to the number of states we have, which is 9, because we want to use a two-dimensional grid to simulate LBM. In this code, we have 4 loops like this, looping over the 9 states to compute something. So this is the for loop we have here. Another loop, as you can see here, it loops over Q states. Third loop here, and the last loop looping over 9 states is this one. As you can see here, these 4 loops are followed by sections of code starting with a comment like this comment, unruled version of the above loop over D. So you can see 4 loops like this, followed by this comment, unruled version of the loop. The unruled code here unrules the loop by replacing this loop, for instance here, by replacing this loop with an inline sequence of operations with less overhead. So as you can see here, we have a loop here, and this piece of code, which is commented, implements the same operation performing by this for loop here. But the overhead of this loop, the overhead of this unruled version is less than what we do in this for loop. This piece of code has less overhead because we somehow we unroot the loop, and we let's just explain what we how we unroot, for instance, this loop. As you can see here in this loop, we want to obtain the sum of all probability distributions and the sum of then we multiply the each distribution, each probability distribution with C constant values, like what we did here. Here we have a probability distribution function and constant C. In this for loop here, we obtain the sum value of all distributions here. So sum is equal to the summation of all distributions. Sum 0, because this Ci here is a vector, so it consists of 2 elements. Sum 0 multiply the first element of constant C with distributions, and the next sum, which is sum 1, multiply the second part of the constant C with distributions, probability distributions. So as you can see here in this for loop, we should access to this vector C and the distribution, this F in vector. In this unruled version, we compute sum 0, and sum 1. But as you can see here, instead of computing these values in a loop, we unroll the loop. And as we can see here, we sum up all the if-in values together. And in this sum zero, we have replaced this constant value. For instance, C00 is 0. The value of C00, if you look at the initialization step here, we can see here that here, as you can see here, C00 is 0. Why? Because, if the, position is 0, so here C0, and as you can see here, I is 0 in the first iteration. So C00 is 0. So here we don't compute this term C00 times F in 0. Why? Because the value is 0, so we don't compute this, and we remove this term. And as we can see here, we remove all the components with the constant C value 0. As you can see here, the number of computations in unruled version is less. And in addition, in loop, we have lots of branches. And these branches add more overhead to the execution time. But in our unruled version, because we don't have loop, we don't have any branch. And it means that this unruled code has less overhead compared with this for loop. So if you look at the unruled version of for loops, you can see that we have replaced this for loop with the unruled version of the for loop. This piece of code performs exactly what this for loop does, but with less overhead. As you can see in the code, implementing the unruled loops are commented out. Here we have loop, but its unruled version is commented out, as we can see here. We can see the same for the other 3 loops. As we can see here, we have a loop here, but its unruled version is commented out. The same here, we have a loop, and here. So first time you use these for loops to simulate the grid and measure time. Then please rerun the code after commenting out all the for loops over D and uncommenting the unruled versions. So in the second run, you should comment these for loops and uncomment the unruled version of the loop. It is expected that the optimized code run faster. You can practically measure execution times of these 2 executions and see how faster the optimized code. So we have 4 loops. I have implemented the unruled version of each loop in the code. First time, you should run the code as it is. Then you should comment these for loops and uncomment its equivalent unruled version. And then measure the execution time of these 2 versions and see how faster is the optimized version. Uh, okay, in the end, as exercise, you want to play with the simulation parameters. As I explained earlier, we have some simulations parameters here. For instance, you can change the size of lattice, or you can change, I don't know, for instance, this Reynolds number. We will discuss this number in next week. You can also implement a parallel version of the model. You can use OpenMP, or I don't know, you can distribute the grid between 2, 4, or 8 processors, and then update each part in parallel.